Wakey, wakey, explorer. The dawn of day 3 is upon us, and as much as I'd love to let you slumber in peace, we have an ocean's depth of work to tackle. Do you recall our incessantly blinking LED from yesterday? Well, today we're going to show those painstaking glimmers of light who's boss. Enter the dip switch. This nifty little piece of hardware will allow us to control the blinking at our will. It's going to be the relentless leash of our overzealous LED. Of course, to make this happen, we're going to need more than just some physical wiring. This is where things get cerebral. We're going to be introducing some conditional logic into our code, a touch of if this, then that. All right then, a flashy switch and some smart code are on our horizon. Rest assured, by the end of the day, we'll have our blinking light under control. So, whenever you're ready, Explorer. Though, regardless of your readiness, we must begin. Right. Let's not dilly-dally. Our main character today is the dip switch. This fellow might look simple with its array of tiny switches, but oh, can it wield a great deal of power. You see, DIP stands for Dual Inline Package. It's essentially a manual electric switch that's packaged with others in a group. The switches are all housed in a single box and can be toggled on or off independently. You may think of this like a tiny panel of light switches, each controlling a separate room in a miniature dollhouse. Each position of the individual switches in a dip switch represents a binary condition, which simply means either on or off, high or low, 1 or 0, yes or no. The magic lies in the fact that you can manipulate these switches to control different parts of a circuit. In our case, the part of the circuit we're so keen to dominate is that perpetually blinking LED. By the end of today, that LED will be blinking only when we want it to. The power of control is within our grasp, Explorer, so let's grab it. Allow me to introduce some vital elements. The ground, or GND, and voltage, or VCC. They are, you could say, the lifeblood and nervous system of our electronics. Ground, my friend, is the common point of reference for all voltage sources in a circuit. It's our zero voltage reference line, the foundation on which all other voltages are built. Without it, our circuits would be aimlessly wandering in the wild, uncertain about where the bottom of the voltage range lies. It also provides a path for our electric currents to return to their source after their exciting journey through our circuits. Now, let's talk about VCC. This little gem is the primary source of power to our hero board. It stands for Voltage at the Common Collector. In plain language, it's the positive supply voltage. If GND is the foundation, then VCC is the engine that powers the machine, the fuel that keeps the circuits alive and kicking. You see, in a system like ours, having a common ground, such as GND, and a common power supply, such as VCC, is essential. It allows different components of the system to communicate effectively, each understanding what the zero and full points of voltage are. This way, when signals or power move between different parts of the system, they all understand the language of voltage in the same way. It's like our own language, really. If we didn't have common reference points and shared meanings, we'd be unable to communicate and collaborate. And we know that wouldn't end well, would it, Explorer? Moving on, the extra resistor. A keen observer, aren't you, Explorer? You see, the extra resistor we're talking about is what we call a pull-down resistor. Its job is to make sure our circuit behaves properly when the switch is off. Without it, our switch being in the off position could cause our circuit to get all wonky. Imagine it like a crowd of electricity not knowing where to go and causing a ruckus. We certainly don't need more chaos around here. What the pull-down resistor does is finish the circuit and acts like a form of crowd control. When the switch is off, it guides the confused electricity safely away, down to the ground. This way, our circuit stays composed and organized, just the way we like it. Remember, Explorer, every brick in a building plays a vital role in keeping it standing. Similarly, every small component in a system is crucial to its overall functionality and success. Now, let's return to our task at hand. Now that we've solved the mystery of the pull-down resistor, let's turn our attention to something absolutely fundamental in electronics, the concept of inputs and outputs. Think of our system as a living organism. It needs to inhale data inputs to process and exhale data outputs as a result. An input is essentially a message received by our hero board. It could be from a sensor, a button, or in our case today, a dip switch. These inputs tell the board what's happening out in the world. In this instance, whether our dip switch is on or off, or high or low. On the other hand, outputs are signals sent out by the hero board. Outputs could be triggered by code conditions or other sensor readings, like the position of a switch. Examples include spinning a motor, sounding a buzzer, or making an LED blink or stay solid. Today, our dip switch is the input, telling the board whether the switch is on or high, or off or low. The LED is the output, responding to this input by either blinking or staying off. Ah, great. We're done playing with our hardware for now, Explorer. Don't look so relieved. The fun is far from over. You already know what's next. Programming our newly created circuit. So, grab another gulp of that precious oxygen and brace yourself for a thrilling journey into the intricacies of code. Let's power through, Explorer. The sooner we do this, the sooner you can get some lights on in here and stop groping around in the dark. Well, Explorer, you've stumbled upon a fairly straightforward piece of code here. Let's dissect it together, shall we? First, we're defining two variables, one for our LED and one for our dip switch. These numbers are currently configured to represent the pin numbers on the hero board where your switch and LED are connected. In the setup function, we're telling the hero board how to treat the two pins we defined earlier. The pin mode parenthesis function is used for this. We will make the LED an output, meaning we want to send out a signal from this pin to control the LED. We will make the dip switch an input, meaning we expect to receive a signal from the switch to this pin. Next, we move to the loop function, the heart of our hero code that, as you know, runs continuously and repeatedly. Inside loop, we have a new kind of statement, an if statement. I can see from the look on your face that cadet training never taught you about conditional logic. Ugh, humans are such ineffectual creatures. All right, time for a bit of theory. Fear not, Explorer, it won't bite. Conditional logic involves creating rules within your code based on certain conditions, much like deciding to wear a spacesuit before you step out into the vacuum of space. Simple. Would you agree? The main tools for this in C++ language are if, and else statements. Let's break them down. If. This is the primary decision-making tool in your code. If a certain condition is true, then some code will run. For example, if oxygen levels are less than critical, we initiate emergency procedures. This only happens if the condition is true. If the oxygen levels are measured to be fine, the code within the if statement is ignored. Else if. This comes into play when you have more than one condition to check. It's like saying, if the first condition isn't true and doesn't apply, we'll evaluate the next one. It's important to note that an else if always follows an if or another else if. Else. This is the last resort. If none of the previous if or else if conditions are true, then the code in the else block will run. It's like saying, if nothing else works out, let's do this. Here's a quick example. You'll notice that we always indent everything inside sets of curly brackets. This simply allows for better readability of the code. In this code, the ship checks the oxygen level and responds appropriately based on the conditions we've set. I hope this brings some light into the murky depths of conditional logic for you. Let's see if we can apply this to our switch situation next. When the switch is on, digital write is executed, turning the LED on, or high, as you could say. This sends current to the LED. If the switch is off, the else block is executed instead. Here, digital write is run, which grounds the LED's circuit, turning it off. So, this code is continuously checking the state of your switch and turning the LED on or off accordingly. Quite easy, don't you think? Now, let's try this out on your end, Explorer. Oh, my. I'll give you credit. You have a keen eye. Good on you for noticing that. You've stumbled upon one of the classic conundrums of programming, Explorer, the tale of two equals. They might look similar, but they have different roles in the programming universe. Let's clear up the confusion, shall we? In programming, a single equals sign is known as the assignment operator. It's used when you want to assign a value to a variable. Think of it as the word is in English. For example, int my variable equals 10 semicolon is like saying my variable is 10. Now, a double equals sign is a completely different beast. This is the equality operator, and it's used to compare two values to see if they're equal. If they are, the comparison returns true. If they're not, it returns false. This is used a lot in conditional statements like if statements. Here's an example. So remember, one equals sign is for assignment and double equals sign is for comparison. It's crucial not to mix these up. Trust me, it'll save you a lot of headache in the future. Oh, it seems to be that time where we cut to the instructional material I was able to gather, cached on the computer. Like the exceptional AI that I am, I've also added this to your mission resources for future reference.
Welcome back, Explorer. So far, we've only used our hero board to blink our on-board LED, and as of yesterday, we've also added the breadboard LED to blink on and off. However, this doesn't really show us all of the capabilities of what our hero can do. In fact, it only really scratches the surface. Not to mention, a light that is always on is always going to be draining power even when we're asleep, and that can't be good for your battery levels. One of the largest strengths of a computer is the ability to examine inputs, make decisions, and then modify the outputs based on those decisions. Each of the pins on our hero can not only produce outputs, they can also be used as inputs, allowing the hero to read the current condition on a pin. I want you to think of the hero board as a mini computer, which it technically actually is, and realize how it compares to the computer that you're using right now. Right now, you're using a keyboard and a mouse as inputs, or potentially, depending on what kind of device you're using, potentially it might be a touch screen or similar, as an input device on your computer. When you click something or you type something in and press enter, that information is sent as an input into your computer. Your computer then does the exact same thing I mentioned before, makes some calculations, and then outputs the calculations on the screen using your graphics display drivers, and you will visually be able to see them on your monitor. Your monitor is an output device, your keyboard and your mouse are input devices. You can think of your computer as the equivalent of our hero board. However, in the case of a hero board, we're going to be simplifying this. Instead of complex mouse movements and large operating system calculations, we'll just be using a simple switch. If a switch is on, and you flip the switch on, you can think of that as pressing a button on a keyboard. The hero, or the computer, is going to then calculate that it needs to do something, and then it's going to send as an output onto another pin. In this case, it's going to be the LED, and then turn it on. So, TLDR, our sketch today will use another hero pin as an input to detect whether our switch is set to on or off. Once we read if it's supposed to be on or off, we're going to turn the light on or off. Let's start by opening the sketch for day 3. As with all of our sketches, the first multi-line comment just gives a lot of information about the sketch. And if you are worried about it and it looks daunting, boop, you can close it just like that. Down below is a few additional concepts that are going to be taught in this lesson. We're going to be learning about the if statement, the else control structure, comparison operators, and digital read. As well as we're just going to talk a little bit about dip switches and resistors. And if that's daunting to you, too many words, don't scared of it, close it up. You don't have to worry about it. I should also mention that there is a few more comment blocks throughout here. If you just want to go here, close, close, close. Once you've collapsed all the comments, if you so desire you want to, what you can do now is you can include the Arduino.h, which contains all the convenient definitions for our selected board. In this case, we have selected the Arduino Uno, as that was compatible with our hero board. If you don't want to include this and you're using the Arduino IDE, which is what I'm going to be using in this example, you can technically hit delete, and if you were to do something like that, then you don't have to worry. It will include it automatically. So if you don't have it, that's fine as long as you're using the Arduino IDE. Otherwise, feel free to keep it. It doesn't hurt anything anyway. Just as in our day 2 sketch, we then need to define a constant to refer to the pin attached to our LED. In this case, we're going to be naming it cabin lights pin, and we're going to connect it, in our case, to pin 12 on our hero board. Then we're going to have another one that we're going to be defining, and it's going to be the pin for the switch, the input device, the cabin lights switch pin. And we're going to connect that to the switch pin on pin 2. For our one-time setup, this is where this is only run once, we need to set up each of the pins to use as either an input or an output. As you recall, the lights, the LED in this case, is going to be an output, and the switch is going to be an input. So here's a switch that we're going to have that's going to be the input, talk to the hero board, and then it's going to calculate and determine that we need to then turn off the LED on pin, in this case 12, as an output. After setup is run, we will jump immediately to loop, as the Arduino IDE and programming language automatically does for us. So we will jump into the loop function, and in here we have a few different versions, and this is where we have commented out because we wanted to show you iteratively how we got to this here. This here is the commented out. We won't be using it, the first version of our loop. It works, but it could be shorter, more efficient, and more understandable. We commented it out just to show you how we can incrementally improve our code. Here we have the byte switch setting, which is just simply going to save if it is on or off into a variable name. First, we're going to say that the switch setting is equal to whatever we read off of the digital read on the cabin lights switch pin. And this is where we can read the state of the light, and we're going to save it into a variable. Digital read is a function that quite literally does exactly as it says. It reads the digital signal off of a specific pin, and in this case, we're going to be saving that whatever it returns into a variable here. So if it is turned on, it should be a 1, and if it is turned in the off position, it will have a 0. That is all that this function does. It just simply determines, is it reading a 1 or is it reading a 0? Is there something being read on the pin or is there not? And so when we save that to this here, it will either have a 1 or a 0. So let's just say if the switch setting is equal to high, or in this case, that's equal to 1, meaning that it's turned on. If the switch is in the on position, then we want to digital write to the LED high, basically turning it on. What digital write is doing here, as we explained yesterday, is it's simply sending a 5-volt signal if it's high onto the pin, or it's sending a ground signal if you set it to low, which is exactly what we do here. If, on the other case, it reads the signal on the pin and the signal was low, then we want to set it down to low. That's the first way we can do it. An improved version that is slightly better is we can remove an extra statement up here, and we can actually add an if-else statement. So instead of using 2 if statements, we can actually use an if-else. So we have byte switch setting equals digital read cabin lights switch pin. This is the exact same as we were doing before, just a little bit condensed into one more line. If the switch setting is equal to high, then we can turn it on. And then else, you'll notice there's no else switch setting equal low, because the only other condition it could be if it's not high in a digital setting is it's only can be low. So we can actually remove that and simplify it ever so slightly here. And even then, with the if else statement, we can actually ignore that as well, because there's actually technically a final version. And this is the one where we're going to be using because it's probably the most simple way that we can implement what was above. We can literally have it as just one if-else statement. If digital read cabin lights switch pin is equal to high, and in this case we're not using an additional variable because there's no reason to have an extra variable that's saved in memory. If digital read cabin lights switch pin is equal to high, then we're going to turn it on to high. Otherwise, if it's not high, Then we're going to turn it to low and we're going to keep the light off. And this is probably the most simple form of what we can get from the above. So with this, you should have all the code that is needed for day 3. With this new functionality, you should be able to turn on and off the LED on your ship with only the time that you need it so that you're not wasting any battery in your critical condition that you are currently in. Best of luck, and we'll see you again on day 4.
Welcome to the wiring example video for day 3. Last time, we saw how to use the Hero controller to raise the voltage on an output pin in order to turn on an LED. Today, we want to build further on that idea with the aim of being able to turn the light on and off at will without needing to reload the software sketch. The key to this is that in addition to using pin 12 as an output from the Hero, we will use pin 2 of the Hero as an input. According to the coding that we've provided in our sketch, when pin 2 reads a high, say, or 5 volt potential, or when it reads low, that is 0 volts, the Hero takes different actions on the output pin 12. There are 2 new points for us to understand here. On the digital side, the Hero is repeatedly executing code in the loop routine, and every time the loop is executed, pin 12 is repeatedly tested, and the status of pin 12 may or may not be changed. The second point for us to think about has to do with how we are going to provide a selectable high or low voltage state to pin 2. Now, in order to do this, we've set up a small circuit on the left side here of our breadboard that runs from 5 volts through an on-off switch, which is this red component right here, then through a high-value resistor. In this case, the resistor has a value of 10,000 ohms, or 10 kiloohms, which will limit the current flowing through it to less than a milliamp, and then finally back to ground to complete the circuit. A quick note, this switch is called a DIP switch. DIP is an acronym for Dual Inline Package, and this is a new component for us. This is actually 3 switches in one package, but we'll only be using one, switch number 1, the one on the left, in today's project, although in future projects we'll have occasion to use more than just one. Now, reiterating, our 5 volts is supplied to one side of the dip switch through this red wire that's connected to 5 volts on the Hero. Now, the switch, in turn, is connected to the high side of our 10 kiloohm resistor, and then that finally completes the circuit back to ground at the end. Now, let's understand how this is actually going to work. If the switch is in the on position, then current will flow through the circuit and through our resistor. The amount of current will be small, but it will be an amount of current commensurate with the 5 volt potential difference between ground and this upper side of the resistor. If we connect this point at the upper side of the resistor using this brown jumper wire, if we connect it to pin 2 on the Hero, pin 2 will now read a 5 volt high reading if current is flowing through the circuit. On the other hand, if we were to throw this switch into the off position, breaking the circuit, then no current would be flowing through, and according to Ohm's law, there would be no voltage difference across the resistor between its ground side and its upper side. So both of those would be at 0 volts. And in that condition, pin 2, connected by this brown wire to this point in the circuit, would read a low. So this is how, by flipping the switch between on and off, we can toggle the voltage at pin 2 between being high and low. Now, I want to make a quick note here before we move on. Our selection here to use a brown wire was completely arbitrary. Depending upon what colors you have available in your parts kit, you might choose to use a different color. Apart from trying to adhere to the rule of using red for positive supply and black for ground, you should feel free to use any combination of jumper wire colors that best help you organize and understand your circuits. There's just one last detail to mention here before we go ahead and test this new circuit. Because we have more than one current loop operating on our breadboard here, we have need for more than one set of supply and ground connections. And this is a situation that'll happen quite frequently. And rather than providing separate connections for our two loops here, our two sub-circuits, we'll set up shared common lines or buses that can be tapped by any sub-circuit on the breadboard that needs to. You'll notice that the two rows along the top side and also along the bottom side of the breadboard are labeled with red and blue lines, and they're special because they are connected horizontally all the way across rather than vertically like the columns in the main part of the breadboard. And since they do connect horizontally all the way across, they provide convenient access to any components that may need to access them from the main part of the breadboard. Notice that in this case, we've really only used the blue bus right here on the top side of the breadboard, and we've used that to distribute ground to our two sub-circuits. So what we have right now is a black wire connected from hero ground to one end of this ground bus. And then we have two places where it's being used, where it's being tapped off. So we have a black wire connecting from this ground line to the lower end, the low side of our LED. So this is the ground side of the LED. And we're also using the same ground line right here to connect to the bottom side, the low voltage side of our logic resistor that's being used to provide a signal to go to pin 2. So finally, we're ready to go ahead and test our day 3 circuit. Now, we're starting right now with switch 1 in the off position. And so we'll upload our software sketch and it'll start to run. But we would expect nothing to happen until we move the switch from open to closed. So let's go ahead and do that. We'll go ahead, go over to the console and upload the day 3 script. So it's loading. All right, the script is loaded now and it's running. And we don't see any change of status until we go ahead and move the switch from open to closed. And so what we'd expect to happen when we do that is that pin 2 will go high, the hero will detect that, and turn pin 12 high to light the LED. So let's go ahead and give that a try. Moving the switch to closed, and that works as expected. And realize now that because the program is constantly polling pin 2's status over and over again, we can turn it on and off as often as we like. So I can turn the switch to off and the LED goes off. And it will respond to any changes in the status of pin 2. So this all appears to be working correctly, and this is just another small step, but we're making significant progress. Next time, we'll build even further on this and get even more complex control over our lighting circuits.